Artificial Neural Networks, Applications to Confined Concrete, Columns, and Shear-in Beams, a video webinar on structural and civil engineering in the digital world. I am Andres Winston C. Oreta, Professor, CE Department de la Salle University, Manila, member of the Philippine Group of IABSE, and Fellow, Association of Structural Engineers of the Philippines. Engineers and scientists, in their attempt to improve the analysis, design, and control of the behavior of built and natural systems, have shown much interest in modeling of the behavior of physical processes. Modeling a system can be causal, wherein the cause or independent data are known and the effects are determined. Inverse modeling, on the other hand, which is more challenging, involves predicting the cause after observing the effects on the system. To model a system, we need data, which can be obtained in various ways depending on the problem. Laboratory experiments, survey, field measurements, or computer simulations. The data is grouped into input and output data, and a model can be derived from this data. The model may be simple or complex and often governed by both known and unknown multiple variables with their interrelationship generally unknown, nonlinear, and time varying. Various approaches have been adopted in modeling. The traditional approach in modeling starts with an assumed form of an empirical or analytical equation, and then developed by regression analysis using experimental data to determine unknown coefficients such that the equation will fit the data. The main problem with this approach is that it is difficult to determine the form and the number of coefficients of the equation, which will best describe the physical process. This approach is said to be model-driven, meaning the solution is restricted to the assumed functional relationship of the equation. With this approach, different expressions have been derived, ranging from simple to complex, linear to nonlinear, depending on the assumptions and the details of the experimental data used by the researchers. Another approach, which is the focus of this presentation, is through artificial neural networks. What are artificial neural networks? ANNs have started to be used in the modeling of various civil engineering systems. ANN have been found very powerful in modeling systems governed by multiple variable interrelationships, especially when the data available are noisy or incomplete. One advantage of neural networks is that there is no need to know a priori the functional relationship among the various variables involved, unlike in regression analysis. ANN automatically construct the relationship for a given network architecture as experimental data are processed through a learning algorithm. Hence, ANN modeling is said to be data-driven. This is an example of an architecture of an artificial neural network. The processing of data in an ANN is shown. There may be one or more inputs to a node. The input data are processed as a weighted sum of the product of the inputs. The weighted sum is activated using a function to produce the output from the node. In an ANN modeling, the connection weights are determined as new input data are processed and new predicted output data are activated, which are compared to actual outputs. There will obviously be an error between the predicted outputs and the actual outputs. The error is processed wherein the weights are corrected to improve the model. The training process is continued until all data are processed and the final model is obtained. An optimum value is determined to determine the final values of the weights. The error of the final model can be assessed using the following error metrics. This is the mean average error and the root mean square error metrics. Comparing the data from the network and the actual data. The figure shows the general steps in developing a backpropagation ANN model. The most important is data. Collect the data and divide the data into training and test data. Step 2, you decide the ANN architecture. How many input nodes, hidden layer nodes, and output nodes define your model. The third step is you train the ANN model using a learning algorithm and the training data. In this process, there is an initial value of the weights, and the weights are modified as new data is processed for the training algorithm. Finally, after the training, you can validate the ANN model by using the test data and the error metrics. You can conduct simulation or parametric studies using the final model to check whether the model produces realistic results. The first application that I will present is about confined circular RC columns. A paper on this application was published in the Journal of Structural Engineering. American Society of Civil Engineers in 2003. Concrete columns, when subjected to axial compression, will develop internal cracks, increasing the volume and resulting to buckling of the longitudinal bars and finally collapse. Passive confinement due to spirals and hoops increases the compressive strength of columns. When lateral expansion occurs, tensile stresses in the spirals, hoops, or closed ties are developed, and passive confinement occurs. So, passive confinement prevents the lateral swelling of the confined concrete. What is the effect of confinement in RC columns? The effect of confinement is an increase in compressive strength of the column as shown in the figure. Columns with more ties, that is, smaller spacing, have larger confined strength. In this figure, you can see the unconfined column with the corresponding strength, and two columns, one with a spacing of 30 centimeters and another with a spacing of 60 centimeters, and you can observe the increase in the unconfined, from unconfined strength to confined strength. So what are the parameters that contribute to the confined strength of concrete columns? Here are some of the parameters that are considered in the modeling. The volumetric ratio of lateral reinforcement, the yield strength of the lateral reinforcement or ties, the unconfined compressive strength, which is determined by uniaxial compressive test, the tie spacing, and of course the arrangement, the section dimensions and the shape of the column, longitudinal reinforcement. As discussed earlier, there are two approaches in modeling. The model-driven, where empirical equations are derived using regression, and data-driven, using ANN. In ANN modeling, we need to define the architecture or number of nodes and determine the weights by using training data. Here are examples of empirical equations derived using regression analysis for the confined compressive strength or the peak stress of the column and the confined strain at peak stress. We have equations by Mander, Satyogli and Rasvi, Hoshikuma, and Sakai, and observe that the form of the equations vary from very simple to a more complicated equation. In this study, experimental data from the following sources were used in deriving the ANN models. The data are grouped into training and test data. Test data are used after the weights have already been fixed and determined after training. There is a condition for a unique approximation. The number of data for training must be greater than the number of unknown weights, and 20% or more will produce good approximations. Here is a sample of a set of data from one of the references. And you can see there are different specimens, the unconfined strength, confined strength, unconfined strength, the dimensions of the rectangular columns, strength of steel, amount of steel, spacing, and the amount of longitudinal columns. The ANN architecture for this study consists of 7 input nodes, which consist of f prime of C, D, diameter, the height, steel strength, yield strength, steel ratio, spacing, and longitudinal steel ratio. And the range of the values of the data from the database are shown in this slide. This will be the range of or limitation of the present model. The output has 2 nodes consisting of the confined strength or the peak stress and the strain at the peak stress. So in this study, the number of hidden nodes were varied, and the simplest number of hidden nodes is considered as the final model. This is a comparison of 3 ANN models with varying hidden nodes. The ANN with 4 hidden nodes was found to have the minimum error compared to the others. So the hidden nodes varied from 2, 3, and 4, and at the n equal to 4, the modeling was stopped and the final model is decided to be the N742 model. You can see here the summary of the prediction errors for the different models, both for the training and the test data. And specifically for the test data, the minimum values of error were obtained, both for the stress and the strain. This is the final ANN model, N742 model, which consists of 7 inputs. 7 inputs, 4 hidden nodes, and 2 outputs. Shown in the table are the weights connecting the different nodes. So for input f prime of C connected to hidden node number 1, this is the weight. For D connected to hidden node number 1, etc. The relative importance of these weights can also be determined, and the significance of this is that the f prime of C has the largest contribution to the prediction of the outputs with 45%, followed by the strength of the steel, the amount of steel, and then the spacing of the ties. The least parameter contributing to the output is the amount of longitudinal steel. Since the equation of the AN model is quite complex, it is very appropriate to develop a computer program. Hence, this is a sample Visual Basic program of the AN model with the 7 inputs and the corresponding outputs, the peak stress and the peak strain. Using this program, simulations, and testing was done. Shown in this figure is a correlation between the predicted and experimental stress with R values of about 1.0. The percent error predictions is less than 10% for 78% of the test data and 90% of the training data. Shown in this figure is the correlation between the predicted experimental strain with R values of about 0.97 and the percent error is less than 10% for 89% of the test data and 79% of the training data. Here is a comparison of the predictions for the confined peak stress for the empirical models and the ANN model. The ANN model has an average ratio of 1.02 compared to 0.83 to 0.99 for the empirical models. For the confined peak stress, a comparison of the predictions among the models shown that there is less scatter for the AN model. This is for the predicted stress, experimental stress, and you can observe that the predictions of the AN model almost lie in the 45-degree line. This is the comparison for the strain, and similarly there is less scatter for the AN model compared to the empirical models. Parametric studies are necessary to check the performance of the AN model, if realistic or not. The first parametric study is the effect of tie spacing on peak stress. The AN model shows that as the tie spacing increases, the confined peak stress decreases, which is as expected. Moreover, it can be observed that the column diameter affects the peak stress value, d equal to 300 versus d equal to 400. There is less confinement effect for larger columns. And the AN predictions are shown with the experimental data from Sakai and Mander showing a similar behavior. A similar trend is predicted by AN model where the smaller strain at peak stress is obtained with an increase in tie spacing. This figure shows the effect of diameter, size, and tie spacing. The column with smaller diameter and spacing shows higher peak stress. So the AN model can qualitatively simulate the effect of D and spacing on strength enhancement for varying f prime of C. This figure shows the effect of the unconfined compressive strength of concrete. Passive confinement is more efficient for lower f prime of C since it cracks earlier, resulting to more lateral expansion. So here the ratio f prime of C over f prime of C decreased from 1.9 to 1.6 for f prime of C 20 MPa to f prime of C 30 MPa. The figure shows the parametric study on the effect of longitudinal bars. This figure shows the minimal effect of the longitudinal steel to the confined concrete strength of the columns. There is a minimal increase in peak stress of about 5 to 8% from n equal to 8 to n equal to 18 longitudinal bars. This figure shows the effect of longitudinal steel to the strain at peak stress. The strain occurs earlier when the longitudinal steel is higher. Conclusion for application number 1. The AN model showed realistic trends in simulating the strength enhancement due to confinement of circular columns. The effect of parameters such as tie spacing, column dimension, unconfined concrete strength, volumetric ratio, longitudinal steel ratio, and can be qualitatively demonstrated using ANN simulations. Application number 2 is related to diagonal shear strength of RC beams without stirrups, and a paper was published on this at the Engineering Structures, the Journal of Earthquake, Wind, and Ocean Engineering in 2004. There's a historical case about shear failure. In August 1955, there was a partial collapse of the Wilkins Air Force Depot warehouse in Ohio, USA. Shear failure of 36 inches deep beams, or about 916 millimeters, at locations with no stirrups and longitudinal reinforcement ratio of 0.45%. However, experiment by the PCA indicates that a 12-inch deep beam should fail at about 150 psi or 1 megapascal. The ACI shear strength says that it should fail at about 90 psi. In the actual investigation, it was found out that the beams, which are very deep, of about 36 inches, failed at 75 psi, which is very, very small compared to the actual or to the design strength of 150 psi. Why did the beams fail at a lower strength than the design shear strength. Designed for shear, stirrups are provided to increase the shear capacity of the beams. And how do you determine the spacing of the beams? The spacing of the beams depends on the shear strength of the concrete beam without stirrups. If VC is assumed large, then we will provide less stirrups, hence the spacing is larger. If the shear strength of the concrete is small, then we need to provide more stirrups, therefore the spacing is closer. So if you over-predict the value of the shear strength, wherein you provide larger spacing, it is possible that your design for shear will be unsafe. The ACI shear equations in our current design code do not consider what we call as the size effect, or the size effect represents the effect of deep beams on shear. As you can see, there is no parameter related to the depth except here, which is directly proportional. The design using the shear equations of ACI may lead to unconservative and unsafe results, especially for deep beams. How safe are our large or deep beams? This figure shows experimental data with varying depth. Estimates of V sub C using the ACI equations for large beams are greater than experimental shear stress at failure. The ACI equations based on experiments of shallow beams, shear strength is not constant, but it should depend on size. So the line here represents the ratio of the ACI equation divided by the experimental shear. Values above this line represents over prediction. Diagonal tension failure is a common failure of beams under shear, especially in slender beams. In diagonal tension failure, characterized by very fine vertical flexural cracks, band failure at the support, and usually the cracks are developed about 1.5 D from the face of the support. It is a brittle type of failure with small deflection. The parameters used in the AN model for diagonal tension failure are shown in this slide. There are 5 inputs in the model: the compressive strength of the concrete, the width of the beam, the depth of the beam, the A over D ratio, the distance of the load to the edge, and the amount of steel, longitudinal steel. The output is the stress, shear stress, which is the failure shear divided by the dimension of the beam. This is the final model after conducting training and testing of the data. These are the parameters with the corresponding range of application of the following present model: 5 nodes, 1 hidden node, and the final model consists of 5 hidden nodes and 1 output node. This is the program, the interface of the program for the final model with 5 input nodes and 1 output node. Shown in this table are the weights, the final weights of the M2B551 model, corresponding to the 5 hidden nodes, and connection weights corresponding to the output nodes. What is the size effect on shear stress? Using the AN model, it can be shown that the size effect is presented as the depth increases, the shear stress also decreases. Trend is consistent with experimental results. The shear failure depends also on the A over D ratio. Okay? A shorter beam, smaller A over D, has a larger shear capacity. The experimental data are shown also in this figure from the experiment of Kani, to show the comparison or the trend of the AN model with the experimental data. What is the effect of F prime of C and beam depth on shear stress? The increase in shear strength is significant in beams with smaller depths. Smaller beams have greater strength than deeper beams for the same F prime of C. What is the effect of A over D? A shorter beam has a larger shear strength than a longer beam, as shown in this figure. What is the effect of longitudinal steel ratio? The rate of decrease of shear stress is larger for lightly reinforced beam. There is a 60% decrease for rho equal to 1% versus 33% decrease for rho equal to 2.75%. These are the design equations from other codes which considers size effect. In Europe, you can notice that in this equation, the D is shown here, no? And it is exponent 1 over 3. No? And the D is a denominator, which means as the D increases, then the shear stress will also decrease. Similarly, in the JSCE equation, the D is also below or a denominator, which means an increase of D will result to a decrease in the shear strength. And this relationship is not reflected in our present ACI equations. Conclusion for application number 2. Shear stress in RC beams is not constant, and size effect must be considered to assure safe design for shear. ANN modeling shows the effect of parameters such as tie spacing, column dimension, unconfined concrete strength, volumetric ratio, longitudinal steel ratio, and shear strength of RC beams for without stirrups. Final conclusion about ANNs. ANNs are data-driven, meaning ANN requires data with a range to develop models with wide applicability. It is non-parametric. There is no assumption about the functional form relating input and output data. It has the ability to develop a generalized solution to a problem from a set of examples. It can model nonlinear and multivariate relationships. Parametric studies are important to verify the ANN performance. Artificial neural networks are also faster in speed for processing, and they are usually robust. It uses highly parallel connections between processing elements or the nodes. Computation is distributed among many processing elements and works well even for noisy and incomplete data. That's all. Thank you very much for your attention.